The objective of this tutorial is to first highlight the common type of lamps that are available for use with atomic absorption instrumentation. These source lamps, known as hollow cathode lamps, are required for each element that needs to be determined with this technique. We'll also highlight the performance and lifetime advantages of Agilent lamps and address some of the common myths that people have about operation and use of hollow cathode lamps. And we'll also provide some guidelines to help users achieve the best performance with the lamps that they're using with their atomic absorption instrumentation. Agilent offers a range of different lamp types. So Agilent hollow cathode lamps are available in either coded or uncoated formats. Coated lamps have extra pins on the base that provide a lamp recognition circuit the instrument can use to identify which element the lamp is for. This means the instrument can locate the lamp and automatically start the lamp, even if it has been placed into the wrong position in the instrument. So it really makes the instrument very much error-proof. Now, of course, if you're looking for a more economic option, then uncoated lamps provide the best overall value. And they're compatible with all Agilent and most atomic absorption systems from other manufacturers. If you need higher performance, if you need to work at lower concentrations and achieve accurate results, then Agilent also offers a range of high-intensity boosted discharge lamps known as Ultra lamps. These lamps use the standard lamp current, but apply an additional boost discharge within the lamp to increase the emission intensity. This allows you to achieve much lower detection limits for the most demanding atomic absorption applications. Agilent also offers a comprehensive range of coded 50mm lamps that are compatible with all PerkinElmer atomic absorption systems. They provide economical operation and match the performance of genuine PerkinElmer Lumina lamps. Agilent lamps provide many advantages for atomic absorption users. Firstly, they provide the optimum performance. A combination of the proprietary cathode composition and unique lamp processing procedures ensures good intensity, good sensitivity, low noise, and long-term stable operation. In addition, the lamps are also designed to give very long service life. And that's due again to the optimum gas fill within the lamp. So typical lifetime for Agilent lamps easily exceeds 5,000 milliamp hours of operation, which means that you can reduce your operating cost and you can also reduce your downtime due to lamp failure. Agilent lamps are also preconditioned, so they're ready for use immediately out of the box. That means you can use them immediately, you can improve your productivity, and you can achieve the optimal instrument performance without needing to do any conditioning once you receive the lamp. The Agilent lamps are also designed to provide improved spectral purity. As we show here in the photograph, all the Agilent lamps have this unique black getter patch, which comes from our unique lamp processing procedure. This is a thin layer of activated zirconium, which helps to absorb some of the impurities that may be present in the lamp during operation. And so that helps to trap those contaminants and improve the spectral purity throughout the life of the lamp. Of course, the other reason for wanting to work with Agilent lamps is all about Agilent quality. Agilent lamps are manufactured in an ISO 9001 certified environment and use proven processing steps. Prior to shipment, every lamp is analytically tested to ensure that it meets Agilent's demanding standards for intensity, noise, and stability. As we mentioned earlier in the presentation, Agilent also offers high-intensity ultra lamps, which are a unique design exclusive to Agilent, and these are designed to improve the analytical performance. They enable the user to improve sensitivity by up to 30% over conventional lamps. They improve precision, And with improved sensitivity and lower noise, that can help you to achieve much lower detection limits. So they're suitable for the most demanding flame, graphite furnace, and vapor generation atomic absorption users. They're usually used with graphite furnace atomic absorption applications, but of course you can also use them with the other techniques. In the Agilent Ultra lamp, we use an additional boost discharge within the lamp to get more excitation, to get more emission being produced from the lamp. To enable us to produce that additional excitation, we need that additional boost current, and that's supplied from a secondary power supply. Now, depending on the type of instrumentation you have, on Zeeman graphite furnace systems, that power supply is integrated into the instrumentation. For other types of instrumentation, you need one of these external power modules connected to the instrument. And then it can be connected directly in through the looming to support operation of that high intensity ultra lamp. So the range of Agilent high intensity lamps can be used with all Agilent atomic absorption instruments, and they provide superior cost-effective performance for challenging applications. On this slide, we wanted to give you an overview of the performance that Agilent hollow cathode lamps can provide. This is based on a competitive analysis that we've completed and is available from the Agilent website. Lamps that require excessive stabilization times, or lamps that never reach equilibrium, can create problems for the analyst. Once analysis begins, drift in lamp intensity can change the analytical signal, introducing significant errors. And this is especially critical at trace levels, where the drift could even be more than the sample absorbance. So on this slide, we're showing first of all the short-term stability for the selenium lamps. And here we're comparing the performance of the Agilent lamp, shown in the light blue color, with a number of other competing lamps. This stability trace is shown after a 10-minute warm-up time. So you can see that while most of the lamps were suitably stable, this lamp shown in the orange color for Photron never appeared to stabilize. And you can see there are also some certainly large spikes appearing in the signal. The long-term stability is shown on this side of the chart. And this is based on the measured absorbance for a calibration standard at a concentration of 120 ppm. These solid red lines show control limits of plus or minus variation from the expected result. The Agilent lamp is shown here in the light blue color. It provides the best overall stability, with the average precision being less than 1% RSD for all measurements over this 1 hour period, compared with the worst result for the Varsol lamp, which was more than 3%. On the lower chart, we're showing the lamp lifetime for both the selenium and the lead lamps. The Agilent lamp, shown in the blue colors, gave the longest life for both of these elements, well over 4 times longer than the nearest competitor for the selenium lamp, shown here, and around 20% longer than the nearest competitor for the lead lamp. So you can see there are some real advantages in working with the Agilent hollow cathode lamps. On this slide, we're showing a comparison of performance looking at sensitivity and detection limits for both the lead and the cadmium hollow cathode lamps. Here at the top, we're doing a comparison of the calibration curves that were generated for lead at the 217 nanometer wavelength. The Agilent lamp gives good overall sensitivity, roughly equivalent to the performance of this competing lamp from SGM. For cadmium, here you can see that the Agilent lamp provides the best overall sensitivity, as well as good linearity. And here the sensitivity is nearly twice its nearest competitors. Of course, the other advantage of the Agilent lamp, as shown by the charts on the right-hand side, is that the detection limits that are achieved, the instrument detection limits that are achieved for both the lead and the cadmium lamps, are significantly better than the lower-priced competitor lamps. So again, you can see that the Agilent lamps provide much better performance. In this case, either equivalent or better sensitivity, and more importantly, much lower or better detection limits. This is another slide that looks at the lifetime, comparing the performance or the lifetime of the Agilent lamps with a number of our major competitors. And here we're focused on the lifetime for arsenic, for cadmium, for gold, for copper, and for sodium lamps. You can see that the Agilent lamp, shown by the light blue bar, gives the longest life for each of these elements, well over 2.5 times longer than the nearest competitor for most of the elements, and about 25% longer than the nearest competitor for the sodium lamp. So again, you can see that there's a significant advantage in working with the Agilent lamps. They definitely provide longer life and a lower operating cost for you as a laboratory analyst. Now let's think about some of the common misconceptions that exist about the use of multi-element lamps with the atomic absorption technique. For example, many users think that multi-element lamps actually have shorter lamp life and actually degrade analytical performance. Agilent offers an extensive range of multi-element lamps, but as we'll show here, they offer similar performance to our range of single-element lamps. Firstly, let's consider that issue about the multi-element lamp giving less lifetime. As we've shown here for the range of multi-element lamps, each of these give a significant longer life. So you can see that there is no concern about short lifetime. It really is a myth. The achieved lifetime, as we show in these examples, is no worse than that for a single element lamp. What about performance? Again, there's a misconception that multi-element lamps will give worse performance. But what we see is that when the lamp is operated at the recommended current for the multi-element lamp, the sensitivity achieved with the multi-element lamp is about the same as that which you get with a single element lamp. You may see a slight degradation in the detection limit that's achieved, but that change is relatively small. So again, you can see the concerns about poor performance of a multi-element lamp is also a myth. Here is another proof of performance for multi-element lamps. In this case, we're looking at a number of elements from this multi-element lamp for cobalt, copper, chrome, iron, manganese, and nickel. Here on the left-hand side of the chart, we're showing these traces which show the short-term stability for each of the elements after an initial warm-up period of 10 minutes. And you can see that, sure, there's a little bit of stabilization occurring in the first few minutes of operation, but then the output, the intensity output, remains exceptionally stable for well over the 1 hour of operation that we're showing here on the slide. On the right-hand side, we're looking at the calibration performance and sensitivity for those elements. In this case, looking at cobalt at the top and nickel at the bottom. These smaller charts that you see are an extract taken from the Flame Atomic Absorption Cookbook, and they show the expected sensitivity that we should get for those elements. These larger graphs show what we've actually been able to measure for a range of different holocathode lamps. So it shows the sensitivity that we achieve for these elements, cobalt and nickel, when using the multi-element lamp. Now, if we compare those values, what we see is the measured sensitivity that we achieve compares very well with the expected result from the Flame Atomic Absorption Cookbook. So this again confirms that there is no performance compromise when using a multi-element lamp and operating it with the recommended conditions for that particular lamp type. So let's think about some important operational tips that we should keep in mind if we're going to work with multi-element lamps. As we've already outlined, one of the most important criteria is we do need to make sure the lamp is operated at the recommended current for the multi-element lamp. And this slide gives you an example of why this is so important. For the lead single element lamp, we have a recommended current of 10 milliamps. But in the multi-element lamp, we actually use a lower lamp current. We also recommend a different default wavelength for that particular lamp, and that's shown in these particular slides. In this case, you can see at the 217 line, there's actually a little shoulder on the side of the peak, indicating there's a small interference there. Now, we could certainly still use that for analysis, but really it's not going to be ideal for your applications. The 283 line shows much better isolation, and that's why it's really the recommended default wavelength for lead in this particular element combination. So if you are going to work with multi-element lamps, they do require different operating conditions, and we need to keep that in mind. So we need to ensure that we're working with the recommended wavelength, the recommended lamp current, and the recommended split width for the multi-element lamp. These may well be different to those that were used if you work with a single element lamp. But if you work with those recommended conditions, then as we've shown in the previous slides, the performance will be equivalent to that which you achieve with a single element lamp. So let's think about further recommendations that we should keep in mind when we're working with any type of holocathode lamp. First, let's think about just general care and operation of the lamp. We need to take care with the lamp. It is fragile, so we just need to make sure that we avoid any undue shock or stress to the lamp. We also want to make sure that we try and ensure there are no fingerprints on the end window of the lamp where the light passes into the optical system of the instrumentation. The oils and grease from your skin can build up on this surface, and that can reduce the transmission of light into the optics, degrading performance. Now, of course, that's even more critical for elements that have their emission wavelengths in the UV region, or for elements that are relative low intensity, such as lamps for arsenic, selenium, and nickel. It's always good practice to allow the lamp to warm up for about 10 minutes at the start of the analysis, just to enable the output to stabilize. And as we've already shown, it's also important to work with the recommended operating conditions. And on the Agilent lamp, as you see here in the photograph, they're conveniently listed on the label on the base, so that you can easily see what the recommended current is, as well as the recommended wavelength and the recommended split conditions. When you're working with the lamp, it's good to monitor the performance. So you should monitor the percent gain value that's shown or displayed during optimization. You can compare that with the typical gain values that we have available from the Agilent website at this link. That enables you to compare it with the typical performance. So then, each time you use the lamp, the gain value should be reasonably consistent. And by monitoring this value, you can track the performance of the lamp. A significant change in the gain value for the lamp can indicate that the lamp is reaching the end of its operational life. If you're working with a graphite furnace system, then we recommend that you align the lamp without the furnace workhead in the light path. So align the lamp first, then place the workhead in position and align the workhead so that you're achieving maximum light throughput through the workhead of the graphite furnace system. Another type of source lamp that we should consider is the deuterium lamp that's used for the background correction system in your atomic absorption system. In the Agilent instrumentation, we use that deuterium lamp particularly in that wavelength range between 200 to 400 nanometers. Above 400 nanometers, we really don't use that because there's no usable output from the lamp. But most of the background that we see is in that range between 200 to 400 nanometers. The Agilent background correction system provides good capability, so it can correct up to 2.5 absorbance units of background. It provides very fast correction with less than a 2 millisecond delay between our readings, and that means we can minimize the correction error that occurs when you're working with the background corrector. Now, there are also some common questions that many users ask about the deuterium lamp. So here are some of those common questions and the sort of answers that we can provide. So many users want to know whether the lamp is always on. Well, the answer is no, because the lamp will only be on when the instrument is being initialized, and then it's switched off unless you're using that lamp for background correction in the current method that you're running. The other common question that we get is always about the lifetime of the lamp. Now, of course, it's hard to quote a specific value because there are so many variables, but typically we see lifetimes that exceed 1,000 hours of operation. But for most users who are working with the background corrector frequently, the lamp will typically need replacement on an annual basis.